Yeah, this is, I think we almost finished the discussion, but this is about how to lay out MOS transistors. You want to make a transistor of width W by L, and this is usually split into a number of fingers NF of width WF divided by L. Okay. So as I said, the reasons are first to reduce source and drain parasitics, okay, and also minimize the effect of gate resistance. Are these points clear? How they come about? So let me show an illustration of, let's say I lay it out as a single finger. So this is W and this is L. An alternative to this is 4 fingers of width W by 4. Okay. So let's say this was the source and this was the drain, and this part of course is the gate. Here the gate is all of these fingers of polysilicon. This is exactly like connecting 4 transistors of width W by 4 in parallel. So if you connect 4 of them in parallel, the total width is 4 times the individual width. So this is WF equal to W by 4 and NF in this case is 4. So let's say the length of this diffusion area, I'm assuming you are somewhat familiar with the layout and the cross section of the MOS transistors. So a MOS transistor is made by having 2 diffusion areas that are separated by the length of the channel, and on top of that you have the gate which is separated from the substrate by an insulator. So this length, that is length of this piece of diffusion, I will call it LD. Now this is a reverse bias junction. During normal operation of the MOSFET, this and this will be, these two will be reverse bias junctions, and a reverse bias junction for the most part can be modeled using a capacitance. Okay, as far as we are concerned, the effect is that of a capacitance. And there is a capacitance of the bottom of this junction, and there is a capacitance to the sides. These are modeled separately because again the depth is not in your control, but the area is in your control. So for instance, you can make you can extend it in this dimension like horizontally, but you can't do anything to the vertical dimension. Like everything else, there is the capacitance is modeled using 2 parameters. One is Cj, which is the capacitance of this per unit area. Okay, this also depends on bias, but right now I am ignoring that. So I can make this small n plus region, I can make it small here or large in this dimension, but I can't go into the substrate. This is into the substrate, that is fixed by technology. The depth of this, this is fixed by technology. Okay, so the junction capacitance is modeled by something per unit area plus what is known as the side wall. Okay, this is the side wall, and this times the perimeter. Let's say these 3 we choose as the source. These 2 are the drain. I mean, I am not showing the wires. It's implicit that this is connected to this through a metal. So this and this are connected through a metal wire, and the other 3 are also connected through metal wires. And this is, let's say this length of this is LD. So length of each of these diffusion pieces is also LD. What is the area of the source here and the drain in case of this transistor? So in this case, the area of the source is W times LD, which is the same as the area of the drain, and also the perimeter of the source is what? And it's also the perimeter of the perimeter of the drain. Okay. What about in this case when we divide it into multiple fingers? What is AS? What is AD? 3 by 4. Each one is 1 by 4, and we have 3 of those things. And this is half WLD. And similarly, PS and PD will have the same factors. Okay. So it is reduced compared to a single layout. In fact, if the number of fingers is very large, both AS and AD will be approximately half of what you see with a single finger. Okay. So you should always divide it, definitely. So these are somewhat peripheral to this course because you will not be doing layout, but these are some things that you should keep in mind while designing. And typically this width of the finger you make it to be a couple of microns. It's more based on layout, how convenient it is to do layout and so on. Like I mentioned yesterday, if you have a width of 100 micron, you don't want a single skinny transistor. It becomes almost impossible to route signals to that. So you divide it into a number of fingers and then you make the aspect ratio somewhat decent so that you can route metal lines to it easily. So approximately it becomes half, and anyway, for in your case when you do these simulations, you should also put the ASAD, calculate these things, PSPD parameters and put it. Okay. When you divide it into a large number of fingers, you won't make much mistake if you assume that the drain and source areas are about W times LD by 2. LD will be 0.36, that is 2 times the minimum length of the transistor. In SPICE, the way you specify transistors is there will be not just transistors, any element can be multiplied up. That is in the, when it puts the matrix, the node equations, it multiplies all currents by n. That's what it does. So if you have this, so you would have specified W, L, AD, AS, PD, PS, and then you have a multiplier M. So everything gets multiplied. That is, the W gets multiplied and all of these also get multiplied. You should recheck this in the manual, but as far as I know, this is what happens. Do you know what it does? I think this is what it does. Okay. Because there are two parameters. One is the number of fingers. That also can be specified, I think, in some varieties of SPICE. And sometimes you just use a multiplier. The multiplier M is used to indicate that if you had a single transistor, there would be some certain currents into the terminals. When you have M, you make that M times that thing. So everything does get multiplied. Okay. But I would still advise you to check the manual just once. What is the resistance of the gate in this case? Let's ignore these extra parts that are jutting out of the transistor. Yeah, it's sheet resistance of poly times what? So in this case, what's the resistance of the gate? Let's ignore the extensions beyond the transistor. Let's just take this part of the gate. Just tell me the resistance of this. It's our gate is W by L times the sheet resistance of the poly. Now, all of this resistance doesn't appear in series with the gate because the gate is also distributed. It's not like the gate is at this end of the resistor and you're feeding a signal at this end. But this is an approximation. So in reality, the transistor is distributed throughout. So you can use a distributed model, but let's not worry about that. So this is the gate resistance in case of a single finger. What is it in this case? So each of these gates has a resistance of WF by L or W by NF by L times RSH, and you have NF of those in parallel, so it gets further divided by NF. So the gate resistance goes down drastically as you split it into a number of fingers. Okay. It's based on those things that typically you use 1 or 2 micron fingers, but some cases you may have to do something even narrower than that. Okay. So this is just some practical information. So when you're doing a project or something, if you lay out stuff, you should do it in the right way. And the other aspect is about matching. So let's say you have a current mirror, and not just for a current mirror, typically whenever you have two transistors whose terminal, one of the terminals is common, you can use this, you can simply use a continuation of this. It's not like you have to lay out two separate units of this and then join it together. Okay. So let's say this has 2 fingers and this has 4 fingers. So what you do is you have 6 stripes of the gate. Okay. These are the gate stripes and this is the diffusion. And in a current mirror, the source is common to the 2 transistors. The 2 transistors, the sources of the 2 transistors are connected together. So for instance, let me, so the common source I call S, and this I will call D1, and this is D2. So I can do this. This is D1, this is D2, this is D2. And also, in this case, the 2 gates are also connected together, but even if they are not, you can use a similar layout. As long as one of the drain or source terminals is common, you can use things like this. Okay. So this is G1 and G2, which happen to be connected in case of a current mirror. Okay, and also in fact drain is connected to the gate. So this way you compact the area. If you just separate it, it's pointless, and also the matching will be better when they are closer to each other. And on top of it, if you look at it, the very last transistor has no neighboring transistors. The ones at the ends. The ones in the middle have transistors on both sides. The ones at the end has transistors only on one side. Transistor gates. Now, this whole fabrication process is also dependent on how one particular thing gets fabricated. Depends on all kinds of mechanical and electrical behavior of what is around it. So, it turns out that this particular transistor will have slightly different characteristics from the ones in the middle. So, in addition to doing layout like this, you also end up having dummy fingers, one or more of them on either side. So, depending on the degree to which you want to match, you at least have one on each side. Okay, and these are not connected anywhere. These are like unused transistors. So, you connect the gate also to ground, and you can connect the drain also to ground. So, no current will ever flow through this, and it's not connected to anything. But it will make sure that all these transistor fingers which are used in our circuit will have the same environment around it. Okay. So, you are talking about the resistance of this part. So, firstly, this doesn't have to be poly, this can be metal, right. So, once you use metal, the resistance of metal is so much lower than poly that you don't have to account for it. So, this can be a bar of metal, and then you have contacts here. And you can do similar things, these dummy transistors, and also using a single common diffusion area when you have other structures, like for instance, a differential pair, you do the same thing. So again, this comes into picture only when you start doing layout. I don't mean that when you have a differential pair in the assignment, you make a complicated layout and then calculate the area and do it. You can just assume that there are two independently laid out transistors. For instance, here the source is common. So you can use that fact to make a more compact area, make a more compact layout. Okay. Similarly, when you have cascode devices, in fact, this lends itself to even better optimization, because typically you don't need access to this node. So you don't need to be able to contact this node. So you can, by using a common diffusion area, you can make the layout very compact, and you can minimize the area of this node and the parasitic capacitance from that node. Any questions on this? Well, there are lots of such practical tricks which you can, there are a couple of books which you can refer to. Also, when you are doing it, you can use them. Okay, one thing is, see, the reason this, I said, this is about 2 times the minimum length. Let's say 0.36 micron in your technology. You want to do that when you want to take a piece of metal and make a contact here. Okay? But if you don't want to make a contact, you can place these two fingers of poly very close to each other. So for instance, to make this type of transistor, so I can have, so let's say this is G1 and G2. So I can have G1 and G2 very close to each other. Of course, there is always a certain spacing that you have to maintain so that the fabrication goes on reliably, but the separation doesn't have to be so far that you can put another piece of metal between them. Okay. So this way it is more compact than if you did this and you put a contact between the two. Okay. So that's what this is in a cascode. Whenever you have a, let's say you have a cascode layout like this, and let's say the width of the two transistors are the same. So this is W by L2, this is W by L1. The lengths can be different. Okay. Now I don't need access to this node. That is, I am not connecting this node to anything else. So in that case, I can use this layout. So clearly, if I do this, I can also use this. But in this case, the capacitance from this node to ground will be more. Now you know that the impedance of the cascode is the GM by GDS of the top device times the impedance seen below. So if you have a large capacitance, you have a lower impedance looking from the top also. So you can have two gate lengths to be different, because you can make one longer than the other. Okay. But the constraint is that the two widths have to be the same. Okay, so far we discussed the characteristics of low pass channels. We know that it causes ISI, and then we also discussed how to make an equalizer at the transmitter. The transmitter is a special case because the input signal to the filter is discrete. In the simplest case, binary, but it doesn't have to be binary, but it will be some discrete number of, small number of discrete levels. Okay. So it's easy to delay such signals and add and so on. So you basically can do the delaying with a flip-flop, and that's what we use to construct a linear equalizer on the transmitter side. Now we will see what to do on the receiver side. And in general, the receiver always in any system is more complicated than the transmitter. Okay, because we've already screwed up the signal. Now you have to enhance it somehow and receive the and correct the signal. So receiver generally turns out to be more complicated compared to the transmitter. Again, here we assume that the receiver needs equalization, right? So there certainly is a class of systems where you don't need equalization. You make a transmitter, you make a receiver, and it works. The simplest thing is the regular CMOS ICs that you use in the lab and so on. Obviously, you didn't worry about whether the square wave becomes a low pass version of the square wave or anything like that. And as you go to higher frequencies, you can do something better by using differential signaling. You still don't use equalization, but you simply use differential signaling and get rid of many of the problems associated with single-ended CMOS type of drivers. So that also works. But then if you go to higher frequencies or maybe worse channels, you will have to do equalization. We assume that we will be dealing with that type of systems here. So what do we have in the receiver? The transmitter drives a channel. For now we assume that the transmitter doesn't have equalizer. We can put the equalization in the receiver. And we also saw earlier that the two are exactly equivalent. You can, as long as the equalizers that we are dealing with and the channel that we are dealing with are linear, you can put the equalizer before or after the channel. It has the same effect signal wise. The only difference will come in ease of implementation and other practical issues. So now there are a couple of options. We can have a continuous time equalizer followed by sampling, and that is followed by decision. So the decision resolves the analog values that you see to the digital values. Now it can be binary, it can have more levels. We'll start off with the binary example, but in general it can be, in case of PAM4, it has to resolve the analog values that it receives here into one of 4 possible symbols. In addition to this, a receiver also will have, will need to determine the clock that you need for sampling, okay? Because you know the frequency approximately, and even if you know the frequency exactly, you don't know the phase. And you can never make the transmitter, there is an oscillator which creates a clock which causes the symbols to be transmitted at a certain rate. And in the receiver, you have a physically different oscillator. You can never make the frequencies of the two exactly the same. So you have to have some method of controlling the frequency of this so that it turns out to be equal to this one. And also the phase should be correct. Meaning, let's say you have an eye diagram like this. You are familiar with this because in the assignment, the output of the equalizer looks something like this. Now it's not just enough to have this, you need to sample here, okay? If you sample here, clearly the signal is almost 0. So this is one possibility, and I'll just say clock and data recovery block which generates the control for sampling. We'll discuss this as we go later into the course, but for now we assume that we somehow have the correct clock with which we do the sampling. So this is one possibility. Another possibility is we sample the input signal and have a discrete time equalizer which is followed by the decision block. What advantages of a continuous time equalizer? So it turns out these are things that we can't discuss in detail now because we don't have the background, but a continuous time with a continuous time equalizer, the adaptation of the equalizer can be independent of the phase of the clock and so on, okay? That is one thing. And the other thing is a discrete time equalizer, depending on the implementation, can consume higher power than a continuous time equalizer. Not really. In the continuous time equalizer also, we operate on the entire waveform, but we still try to make the waveforms at the sampling instance to be ideal. Not necessarily for all time, okay? So that's the, but firstly there is a big difference in implementation. See, one in a kind of vague way I can tell you that. So here you have the sampling followed by the equalizer. So even if the sampling wasn't working properly, you can have the correct signal here, and roughly speaking the clock and data recovery circuit will work independently of the equalizer. Whereas in this case, if the samples were incorrect to start with, your equalizer output will be bad, but the clock and data recovery circuit, it may be dependent on the output of the equalizer. In this case, you have some kind of chicken and egg problem. I mean, this kind of system will work It has been shown theoretically and practically. People have made these things and will work. But you can somehow get a feeling that this is a little more complicated than the first one. If the clock and data recovery is dependent on the output of the equalizer. Because the equalizer won't work if the sampling is not correct in the second case. Whereas in the first case, the equalizer is independent of sampling. Yeah, that relates to how we choose the coefficients of this. So you can make the waveform look overall somewhat better, but then let's say you use this minimum mean square error technique, then it is at that point that you minimize the mean square error. So yeah, for that you do need to know the sampling instant. Okay, but with a continuous time equalizer, if the sampling phase changes by changing the coefficients, you can make the error minimum at the new sampling phase. So I mean, these are some things that we can't discuss effectively without knowing something more about clock and data recovery and so on. Okay. But at least one part that can distinguish the two is implementation. This is a continuous time filter, this is a discrete time filter. So the power dissipation and those things can be different for the two implementations. Okay. And let's again think of FIR type of responses, that is 1 plus A1 Z inverse, B1 Z inverse plus B2 Z inverse square, or if I have to write the same thing in the continuous time in the Laplace domain, I will do, and so on. Okay. How would we implement this? So we'll only consider responses of this type. There are other types of continuous time equalizers that can be realized, right? There can be, just like we saw for the transmitter, we can make other kinds of continuous time filters. But first let's focus on this type of responses. How will we implement this in the continuous time? Transmission lines. So we need to delay the signal and take a weighted summation of the delayed signal. And to delay the signal, we need to use a transmission line. Okay. So I'll call this a continuous time FIR filter. So if I have a transmission line of an appropriate length, I can realize a delay of Ts. Okay. So let's say I have 3 such sections. So I can take the weighted summation. Okay, and that will be equalized, and by varying B0, B1, B2 and B3, I can change the response of the filter, or equivalently the time domain response which can potentially cancel out the intersymbol interference that's introduced by the channel. In fact, if you implement it like this, it's you already carried out the exercise for the transmit filter, but like I said, if you have a linear filter, it doesn't matter whether you put it in the transmitter or the receiver. So the coefficients that you calculated in assignment 2 will hold if you put the equalizer in the transmitter or the receiver. Okay. So it will work here. So that's all that's there to it. The practical problem with this for integrated circuit implementation, or in general for any implementation, is the implementation of the transmission line. Okay. So if you have an ideal lossless transmission line, it will simply give you a pure delay and it will not attenuate the signal or something. Whatever signal appears here, appears at this point A, appears at B after an interval of Ts. But in reality, the transmission line will have a loss. And also, what is the length required? Let's say we are talking about the assignment problem, 1 gigasample per second. What is Ts? 1 nanosecond. What is the length of the transmission line? You need to implement this. Is there some idea? Okay, what is the speed of the wave? Okay, assume something. Like speed of what wave are we talking about here? Speed of light. Okay, so let's say it is speed of light speed of light obviously depends on the medium. Let's say it is speed of light in vacuum. Then, or air. What is the length you need? 0.3 meters. So the speed of light is 300 meters per microsecond or 300 millimeters per nanosecond. So to make 1 nanosecond delay, you need 300 millimeters. Now, if you make it on chip, it will not be in air, but it will be on the insulating material will be silicon dioxide. Okay. So how does that change this? It will reduce it by epsilon. It will reduce it by square root of the relative product of relative permeability and permittivity, and this is 1, and epsilon r is approximately 4. Okay, it's 3.9 or something. So it becomes 150 millimeter. Is this okay? The permittivity of silicon dioxide is about 4. So the speed of light in silicon dioxide is 150 millimeters per nanosecond. So you need a 150 millimeter long line. Is that a large or a small? I mean, what is your idea? Is it 150 millimeters? It seems like, is it large or small? It's ridiculously large. I mean, you can't make, you certainly cannot make it as a straight line, but even if you do this meandering, it's very large. I mean, what is the size of the transistor that you use? Because yesterday someone was saying we are getting very large things of 100 microns or something. So this is much larger than that, right? So you can't implement this. What can you do? So we have not discussed transmission lines properly, right? Characteristics and so on. We'll come to that at some point. We'll go through transmission lines in a little more detail than we have. But give me some ideas on how you might implement transmission lines. Cascaded LC sections. So actually the model of a transmission line, when you are analyzing it, you probably remember that you would use something like this, right? So you split up the transmission line into infinitesimally small inductance and capacitance, and you write the equations, and that gives you the equations for the transmission line. So instead of that, you can just make or mimic the transmission line using this type of structure. Okay. You use lumped inductors and capacitors, and you put a number of sections together, and it behaves like a transmission line. Basically, it's a filter which has some delay, and what's the difference between this transmission line and the actual ideal transmission line? What will be the difference? What might be the difference? Loss? No, there is. Let's assume that this L and C don't have any loss. So I have a system like this, and ideally I would want a transmission line like this. What is the difference between these two? What is the frequency response of this? Yeah, what is the frequency response of the, that's correct. What's the frequency response of the bottom circuit? The magnitude response? So this is a transmission line of impedance Z0, and it's terminated by R equal to Z0. What is the frequency response of this? Have you seen these things? What is the frequency response? Okay, I mean, what does it look like? What's the period? I have a transmission line Z0. It's terminated with a resistance equal to Z0. What does it look like from here? It looks like a resistance Z0. So what is the frequency response of this? We have the, yeah, that is R. That also is Z0. Half. So it is flat. It is constant with frequency. So if you terminate it with the characteristic impedance of the transmission line, you will not see a periodic thing, meaning it is flat. If you can also think of the flat response as a periodic response. If you have a different R, then it will have some response that is not flat but that is periodic. So in this case it is flat. What will it be in this case? In case of the lumped LC, what is the response going to be? What kind of filter is it? What type of filter is it? I mean, is it low pass, high pass, band pass, any other pass? Low pass, clearly, right? You have series inductances and shunt capacitors. So it will short out the output signal. It will also block the input signal. So the main limitation, as I mentioned earlier, is that the range of frequencies over which this behaves like a transmission line or a delay is much smaller than if you use the real transmission line. But we will come to the details of it afterwards. So the one is, and even this occupies large area. Maybe it is not as large as this, but it still occupies a somewhat large area on a chip. Okay. So some of the problems with implementing this are firstly that the real transmission lines will have a loss, and certainly there is no hope of making a strip of wire and that acting like a transmission line because you need a very large area to implement that. You can make lump circuit equivalents, but even that will have a somewhat large area. Okay. And also the other aspect is that the inductance will always have a series resistance, or even if you make a transmission line, it will have a series resistance and it will have loss. Okay, those are the two problems. And one more problem is that, for instance, you had the transmitter equalizer implementation. What happens if you change the clock rate? Will the equalizer response be the same? So you had certain implementation of the transmitter equalizer. That is, you have D flip-flops and transconductors. You add the outputs of the D flip-flops together. So what happens now? You made an equalizer for 1 gigasample per second. Now I want to operate at let's say 0.8 gigasamples per second. What should I do? No, that may be. Let's say coefficients are fine. But what do I do to change this? Delaying should be different. But how do I make the delay different? So I simply change the clock, right? If I, instead of feeding a 1 gigahertz clock, I speed a 0.8 gigahertz clock, it will become, all the delays will become 125 picosecond, 1.25 nanoseconds instead of 1 nanosecond. And you will have the equalizer at the other data rate. Okay. Now if I make it with transmission lines, what do I have to do? So basically it is not really possible, right? We can't easily tune the delay of the transmission line. A delay of a D flip-flop is defined by the clock edge, whereas the delay of the transmission line is defined by the length and so on, which we can't change electronically. So if you are operating over a range of data rates, it's also hard to adjust this. Okay. This may not be a big problem. Many times you operate over a very narrow range, but if you do operate over a wide range of data rates and you need equalization, this may be hard to implement compared to digital or at least a delay line type of implementation where the amount of delay is determined by some clock edge. So by changing the clock frequency, everything scales. So a continuous time equalizer, let's say you adjust the coefficients to get this type of response. Now you can't really change the delay, so the response will always be like this. So if you, so the response will be just fixed. But if you have a digital type of implementation in the transmitter, if you change the clock rate, so let's say this is half, that is F by Fs is half here. Now if I change the rate, then the F by Fs will move to this and I will get the same shape but scale to a different frequency. If I do a sample data implementation, the response is a function of the normalized frequency F by Fs. So you can't tune it very easily. That can be a potential problem with continuous time FIR filter implementation. Okay, I want to make, let's say we saw this and we'll see how more details of how to implement that later. But how do I make a discrete time filter in the receiver? Sample and hold. What do I do? A sample and hold is just schematically just this, where this is periodically clocked. And what do I do? I want a similar response, B0, B1, B2, B3. Quantize this. Okay, we need 3 or 4, so I can connect another one. So we have to buffer it. So this is a buffer. This is a buffer. So I have something like this, and I can take these B3. The diagram is not very neat, but I think you get the idea. So by summing the outputs of a chain of successive, cascaded sample and holds, we will get an FIR implementation. So all these buffers are assumed to have a gain of 1, and all these sample and holds are operated synchronously. Okay, they all sample at the same time, but you can see that the sample here will be 1 sample delayed compared to this, and so on. Okay. So this is one way of implementing a discrete time analog equalizer. So we make a sample and hold. Sample and hold again is the timing is defined by the clock, the sampling instant. So if you have a cascade of sample and holds, then the successive sample and holds hold values that are delayed in time by 1 period of the clock. Okay. By doing this, we can get an FIR implementation. What are potential problems with this? Summation block, okay. How do we implement it? Or yeah, we'll see that soon. But we can do it like we did before, right? We can have, how did we do it in case of the transmitter? Sure, yeah, you need linearity. Whereas before you could use transconductors in their switched regions, now you need them to be linear. That is, the output current must be proportional to this. That's true. But besides that, you can use the same approach, that you have a number of transconductors which are connected to the same output nodes. So the current sum, and then that passes through certain load impedance. Then what else can you do? You were saying something about quantization? Yeah. So the other kind of brute force approach, which is really a digital implementation of the same thing, is you have an A to D converter. and the sampling is inside the A to D converter. Okay. So at you sample the input signal and you quantize it. So the output of the A to D converter is a digital signal. It is quantized in amplitude and also quantized in time. This comes out at a rate fs, and you get a certain number of bits. And once you have it in digital format, you can delay it using registers and so on. Okay. Once you have registers and any other storage element, you can do the storage and computation. This is really a digital implementation of the filter. So you convert the analog input into digital words, and digital words can be delayed and stored. You can do whatever you want with digital practically. Then you can do the delaying and summation in the digital domain. So these are all the different possibilities. What is, yeah, so one question is, what should be the accuracy of this? I mean, clearly the higher accuracy, the better it works, but I mean, that entirely depends on the application. Okay. So for instance, in the Ethernet, if you have a gigabit Ethernet card, that uses an architecture of something like this, and in that case, Zen is of the order of 8 to 10 bits you need accuracy. There, because the equalizer is very complicated, they tend to use digital implementations of the equalizer, but before that you need to quantize the signal, and the signal is quantized to 8 to 10 bits. Now if you go to very high speeds, basically it depends on how elaborate an equalizer you need, that is how bad the channel is. Okay. So if you go to a very high frequency, maybe the channel characteristics is not as bad, but it's just a high speed implementation. So you really cannot make a high speed A to D converter with a lot of accuracy. So there maybe 4 or 5 bits is enough. The problem with this type of approach is that the A to D at a very high speed takes a lot of power. So because of that, you may be better off going to one of the other implementations, using either sample and holds or some combination of continuous time and sample and hold equalizer. So this works. The trick here is to make the A to D. Okay, if you are operating at, let's say, 10 gigasamples per second, the A to D has to work at 10 gigasamples per second, so that can be a very power hungry block. Any questions? So what we'll do next is to look at how to choose the coefficients of the equalizer. Meaning, if you know the channel, we already know how to do that. Whatever works for the transmitter works here. But now here we'll go on to adaptation. The receiver will have to automatically adapt to whatever the channel is, and then adjust the coefficients automatically. We'll look at those things. And after that, we'll look at how to implement some of these equalizers.